Yeah, so welcome back to Cloud Computing and Big Data, the second part of Lecture 11, Big Data Analytics and Cloud Data Mining, given by Chadi Barakat. So please continue, Chadi.
Okay, thanks, Morris. So we talked before about association rule mining and how it can be applied in the cloud, and how sometimes it's necessary to apply it in the cloud because locally it might seem impossible. So for the next step, for the next part, we're going to talk about deep learning. And I know this is not a deep learning course, and bear with me a bit because I might talk about some technical details. But mostly, this is not actually just the application of deep learning and trying to find new things. It's mostly using deep learning to generate data and to also analyze data so that we can have something. Well, mostly it's just to support data. So what I'm trying to say here is mostly that this is not something that the user in the end will be seeing happen. This is something that's going to happen in the background to generate some labels, to maybe improve the whole process. And this is the kind of stuff that you work on when you're trying to apply deep learning in cloud computing or in big data. So let's get into it. So you might have seen this already, which is when you go on some website and they ask you to prove that you're human. Right now, it's just this this kind of thing, which is I'm not a robot, but sometimes you get this kind of small window that appears that asks you to tell which pictures have a stop sign in them, or maybe a fire hydrant, maybe crosswalk, like here in this case. Sometimes it tells you where's the number plate of the car. And you might be wondering, like, okay, fine, the main purpose of this is to prove that you're a human, but why is it this kind of pictures? Mostly, this is something that's happening in the background, which is mostly Google collecting labels from you, using everyone on the planet, technically, to collect labels about these kind of pictures. And these will be used to train their algorithm that's going to teach a car, the self-driving cars, to tell the difference between a pedestrian walking on the street and just a pedestrian walking on the sidewalk, or the zebra crossing for when you're trying to cross the road, or how to tell where the fire hydrant is on the street, or how to read the stop sign. So all of this is just background data mining. And this is done using deep learning. So again, I say this is not user facing because you're not, the deep learning algorithm is not being applied to you. It's being applied to the data that technically the user is supplying. So mostly these algorithms, these deep learning algorithms, they're going through online databases and looking at the images and trying to generate labels and tags for these products, or they're going through Wikipedia or recorded sessions or open access literature that's available online and trying to come up with, to improve natural language processing, or they're just going through databases and applying some kind of association rules to these databases and trying to extract from them some kind of associations. So all of these are happening right now in the cloud. And this is what we're going to talk about specifically in this part. So to start off, let's just go back to previous lectures. And we, like in lecture 6 by Dr. Gabriele Cavallaro, he talked about the difference between shallow learning and deep learning, and he defined it as, well, shallow learning is any learning network that usually have at most 1 or 2 layers, whereas deep learning is that the layers get deeper and deeper and deeper. And as you go deeper through these layers, the object that the network is looking at becomes more and more abstracted. So you, instead of looking at the whole picture, you're just trying to define parts of it so that you can have more understanding or a better understanding of the thing that you're looking at. So if you want more information about this, please go to lecture 6. But for now, we're just going to move on because this has already been covered. So in our case, working with the On4Off project, we have these 6,000 or 7,000 pictures of perfume bottles. And again, us as humans, we have these millions of years of evolution behind us that allowed us to tell the difference between one object and the other, to try to find the berry from in the bush, like to find the contrast between red and green, or red and black, like to see these things that would like right now they draw our attention and we're aware of them, but we had to go through millions of years of evolution to get to this point. And to do that, we do that automatically, but to train an algorithm to do that is a lot more difficult. So how do you do that actually? So for us, we look at this picture, at these pictures here, and you see, yeah, this bottle of perfume looks like an old-fashioned one. This one looks like a magic lamp. This one looks like a bottle of whiskey. Some of them might look like fists. Some of them look like a skull or a diamond or whatever. We can tell that automatically. We're not saying that this is a bottle of perfume. We're saying something that's more abstract. And our job right now is to teach a computer to be able to do that, or a neural network to output some kind of label like this for these products. Technically, the main goal of this is when you're going to the shop and you don't remember the name of the perfume, the first thing you say is, it's that perfume that looks like a gold bar, and or it's this perfume that looks like a teddy bear, or it's this perfume that the bottle was green and it was shaped like an apple. We can do that automatically because we have these kind of associations in the background, in the back of our minds. So we don't want a neural network that can tell us that this is a bottle of perfume. We want this network to come up with these abstract ideas. And this is the process of doing this, is actually building an actual network that can tell in the first place what the product is, and then trying to make it a bit more inaccurate. So generally, to do that, you have to exactly understand your problem. And these are the first few steps of any machine learning problem, which is to first of all understand your problem, and then look at your data and try to understand what your data is telling you. And then you go back to understanding your problem. So I have this data now. How can I apply this data to the problem that I'm trying to solve? And then you just keep going through this whole process until you eventually come up with an idea of what you're going to do and how you're going to do it. And this is part of the CRISP-DM documentation. The CRISP-DM, which is the cross-industry platform, cross-industry standard for data mining. And this is this is probably one of the most important tools that you can have in your tool belt for any kind of data mining project. And I really encourage you to go through the bibliography at the end of this lecture and to go through the CRISP-DM process. But anyway, the main idea of image processing in deep learning right now is using convolutional neural networks. And these are really good at analyzing pictures and extracting features from them. But an actual better algorithm is the ResNet algorithm, which Gabriele and Rocco already spoke about in their lectures. And ResNet specifically is pretty good because it's trained on these 1,000 classes that are listed in the ImageNet database of images. And these are the 1,000 most common objects in any language, mostly animals, species of dogs, objects, some abstract ideas, but it's just a very valuable tool for anyone who's trying to train a network to recognize what an image contains. So our approach is mostly, we first try to apply ResNet 50 to the images that we have from the suppliers. These images of perfumes, we try to run them through this deep learning algorithm, and we got this kind of results, because mostly running a deep learning network is pretty easy. It doesn't take much resources, and it's just 2 or 3 lines of code. In this case, all you have to do is just load the modules and then build the network, and then input and in just this case here, this is, you make the model, and then you pass an image through it, and it predicts. And you can see here, for the bottom 3 pictures, these 3 pictures, the algorithm immediately predicts that this is perfume. And that's great. That's kind of scary as well, but that's not what we're looking for. And even in this one here, it predicts it's a teddy bear. But again, we don't care. We're not looking specifically. We're not looking for specificity. We're actually looking for abstract. And then if you look at the less common predictions, then it gets interesting. So for example, here, table lamp. Now that I think about it, yeah, it does look like a table lamp. This would be the, I think they call it abajur, the part where the lamp would be. This one, it predicts it might be a beaker or a red wine. Yeah, for me, it looks like a decanter for red wine, but yeah, it rings a bell. And for this one, it says it might be a cocktail shaker or a spotlight, maybe because of all the white values in the picture. So that seems interesting at this point. Sorry. This is where it gets interesting. In this case, some of the words are weird. Seatbelt. I don't know why it would call it a seatbelt, but regardless, it's interesting. So in this case, our approach was, this is good. We'll take these secondary predictions and we'll use them. But we're not going to use them actually as the labels themselves. We're going to use them to train our own network. And this is the whole idea of transfer learning. So transfer learning is the process of adapting a pre-trained network that has already all of the weights established and all of the calculations already done. And then we take it, and then we remove the bottom layer of it, the top layer, which is the classification layer. So in the example of ResNet 50, it has a classification layer that has 1,000 classes. And we just discard it. We don't want this because we don't want to classify over these 1,000 classes. We want to classify over our own classes, which absolutely have to be related to these original classes, but they don't have to be the same ones. Just we're applying a new task to an old network, but it has to have some kind of common ground with it. So this new classification layer that we establish is trainable. But the rest of the network, we don't need to train it at first. What we do is just run it again and try to train this final classification layer over our original pictures. And we see, if our results seem satisfactory, then great. We provided a list of good results We provided for training, and then we see what kind of output we have. If the output is not okay, if the output is not effective, or if the training isn't running well, then we go back to the ResNet, and then we unfreeze some of the layers, and we try to train them. So since ResNet 50 has 5 convolutional blocks, each of which has 10 layers in it, for example, we go through them one by one and try to change these weights based on our new classes. And we see how that affects the training process. And that might give us some very good results. But here we run into the other problem, which is computational cost. Because the basic ResNet 50 has 25 million trainable parameters. Running it normally is just a doozy. It doesn't take much effort. But trying to train them, I mean, I would say it's impossible to run it on a like a basic machine or a basic laptop. I tried it, and mostly the prediction was that it would take maybe 1.5 years to finish. And that's not feasible. So that's why you need access to some more adapted resources. If you want to train your network using transfer learning, you have to have access to some resources. Sometimes your project is funded by some European source, and you have access to large-scale computing, and that's amazing, that's great, but that's not something that everyone has access to. So you have to rely on some cloud services. And this is where Amazon Web Services and Google Cloud and Microsoft Azure come into play, because they offer this. I mean, Google Collaboratory has some of these resources for free, but sometimes you need more. And sometimes you might have access to the resources, but you need some proof of concept. And the proof of concept that you need to have, you have to do it through one of these resources. And it's amazing that this is possible right now, because before, all of this research would have only been possible through grants and through a lot of ups and downs in the industry. So it's amazing that this is possible right now, and so easily. On the other hand, there's the other problem, which is that, yeah, maybe you have good labels, maybe you can train properly, but your pictures aren't good. And then you just go through the question that is at the center of all research, which is, what if my data is not enough? So the most obvious answer is get more data. But I mean, if I could get more data, I wouldn't be having this problem. Then the other problem would be, should I train on the same data over and over again? And no. So then the answer, the least obvious answer would be to generate your own data, generate fake data. And this is something that we actually do. And here's an example of generating fake images from the images that you already have. So data augmentation, specifically, we're talking about image data generator, which is part of the Keras module in Python. This is a process of, instead of you generating your own images, it's actually during every step of the training process, this algorithm creates images automatically. And it can shift them, it can rotate, it can flip. And this is just another way of creating new data from the stuff that you already have. So instead of having just 6,000 images in our case, you would have maybe 100 copies of each image, each of them shifted in a way that the algorithm has new details to know about it. So you make your algorithm, you make your deep learning network a bit more efficient, a bit more effective at localizing and then understanding the content of the image. But again, this is also computationally expensive. So this is also another way that you need these cloud resources. And the last part um, of the work that we're doing with images is the color detection and classification. And this is not an application of deep learning, but this is an application of another type of machine learning, which is clustering, and another type of unsupervised learning. So again, we as humans were able to detect color, again, because of like this contrast, this ability to tell contrast. Our eyes are adapted to seeing red and green, and that's been very helpful. But computers don't have that ability. So how do we teach them? The answer is mostly don't teach them, because sometimes the most obvious answer is the easiest, and sometimes the easiest answer is the best. So this is the concept of Occam's razor. The simplest solution is probably always the best. So instead of training a neural network, just put an algorithm that takes less than a second to run, and it just produces equally good results. I don't need to train a network for hours and hours that will tell me the color of this picture, if I can do that with an algorithm that's just out of the box. But it's not something that someone can teach you to be able to recognize. It's something that comes with experience. At some point, you'll sit down and you look at your project and you think, well, I can do this. I know specifically that I can train a neural network to recognize the tiny differences between gold and ochre, or I'm not good with colors, but these tiny details. But is it worth it? Is it worth my time? Because also my time is worth a lot of things. So essentially, your experience allows you to tell which solution is the simplest, and it allows you to make these kind of decisions on the go. So unsupervised learning is this higher level of data representation, and it's just a way of telling the computer, this is your job, do it, and I don't need to give you input. You should make your own input, and you should test your own outputs. And this is something that you can go back to lecture 1, because we talked about it in that lecture slightly. But there's really no need to go into the details of it. It's just a way of finding patterns where they don't necessarily exist. And clustering specifically is finding distance between points and trying to group them together in a way that makes sense. There are several different ways of clustering, several different algorithms. But in our case, when we're trying to find the color of a picture or the color of a perfume, we're going to use the simplest way, which is k-means. And k-means usually depends on Euclidean distance, which is mostly the root mean square. I think that's what it's called. And it's just the distance between 2 points. So to do that, mostly you look at the picture, and you have all of these pictures are in RGB. And you look at it, but clustering over RGB is not usually the easiest thing to do, because you have to find the relationship between every one of these 3 values for every image. So you have to find the relationship between R, red, green, and blue for this image. And then compare this relationship with the relationship of the red, green, blue values of another picture. I mean, it's something that you can do, but why waste some time and effort on this when instead you can approach it from a different way? A different way of expressing color is using the HLS system, which is hue, light, and saturation. Hue, light, saturation is mostly one component, which is the H, the hue, tells you which color it is, and light and saturation tell you how bright and how strong it is. So instead of looking at 3 parameters and then comparing them to 3 other parameters, you're comparing 1 to 1. So your clustering algorithm will have to look at the distance between the hue from one picture to the hue in another picture, and trying to group them together, or like the hue from one corner of the picture to another corner. And that way you can extract which color is in which corner. But how can you tell which color is where? And how can you tell what color is what? This is something that goes back to mostly you Google it, but it's also something that exists in every Linux machine. It's a file called rgb.txt. This file exists on literally every Linux machine, and I'm pretty sure it also exists on Mac, but I haven't checked it. But this file has a list, as you can see here, of all the RGB values and their names. And these values can easily be converted to HLS, and then it's fed into your algorithm. And then the picture is fed through this conversion, and it's fed also into the algorithm, and can be clustered based on these values. So then you know that this picture mostly contains red, but it also contains white, which is the background. Or the bottle of perfume, like the ones we had before. The pink one, yes, it has pink, but it also has the white, which is the reflection in the glass. It also has some kind of blue. It also has some different colors running in it. So that's a way of filtering through these colors, but also exposing them. And with that, you're creating data that can be used as labels for these pictures. So when a customer comes into the room and asks for this bottle of perfume that's gold colored, then you have a tag on each product that has this color. And this tag simplifies your search. Now, the main idea that I have to get through here is mostly, you're applying all of this research, but who am I to tell you about this? I mean, I said in the beginning that my PhD is in bioengineering, but why am I talking about perfume and picture analysis and classification rule mining? And the general idea here is that you apply your knowledge everywhere, and you try to extract knowledge from it. You get some experience, and let's not kid ourselves. Commercial applications pay a lot more than anything else, because there's a lot of money in this. There's a lot of money in understanding the market and understanding what the customers want. And from that, you get this knowledge, and then you apply it to your field. In my case, we're working with medical data in parallel with all of this work I'm doing for commercial applications. We're looking at medical data, especially with the MIMIC database, which is a database of ICU value of physiological parameters from ICU patients. It also contains X-rays. It contains blood tests, respiration data, all of this. And having an algorithm that can crawl through this data and try to extract some interactions between the values, or some association between when a drug is given and what effect it has, but also when a drug cocktail is given, if it has more or less effect, or when this kind of ICU drug is given and the patient has this value, so when A and B are present together, then this patient has a higher chance of improving over time, or a less chance of improving over time. So this kind of classification, association rule mining, but in the medical field. But I would never be able to do this if I didn't have this basic understanding of this process by applying it in commercial applications. And the same goes for deep learning. Deep neural networks are right now, as we're speaking, being applied for COVID analysis. They're being applied to chest X-rays from that are publicly available, and you can go through the bibliography for this. And it's quite an interesting read. They're crawling through international open source databases of chest x-rays and trying to train a neural network that detects COVID from the differences in the granularity of the pictures, the chest x-rays of the ICU patients. Their data set contains maybe 6,000 images of COVID patients, but 18,000 patients of, I think it was some other kind of pulmonary infection. And it's amazing to see this happen in real time when you're actually working in it, but it tells you how important it is to be able to process all of this data and to also apply this modern technology in this field that, I mean, you realize how important it is right now. We desperately need some kind of way of quickly and easily diagnosing patients. So all of this process is to tell you that any kind of knowledge that you get in the field of data mining and cloud computing, it can be applied in your field, no matter what it is. It's just based on your understanding of that field. And I guess with that, we're done for today. If you guys have any questions, I would be willing to take them, but I don't know if Morris would like to make a conclusion to this.
Yeah, maybe you can also go through the lecture bibliography, just, you know, swipe around it, that the people that see it then on YouTube and on the recording also see that don't have the slides. But first of all, Chadi, very nice lecture, very great, basically covering a huge wide variety of algorithms. You know, we have seen in the beginning the association rule mining, where we had FP growth because it was scalable, but also simple models like a priori. And then we had a different light on data mining, saying that deep learning can be also used as a non-user facing algorithm, right? Which was interesting to see that essentially we just fill a database with tags which are not there. So you have a question from a customer in a perfume store, and he says, I would like to have a perfume. It looks somehow like a gold bar, but actually I don't know the name. So what you do, the database doesn't refer to the look and feel of the bottle with gold. It doesn't say any shapes. So you could use deep learning, as actually Chadi was pointing out, to just fill the database to be able to respond to questions like, I want to have a perfume that is basically looking like a gold bar. And of course, all the database would list, yeah, there is a perfume Paco Rabanne, which is called like this. But if you have a question like this and you don't know the name, then this helps enormously in a real practical situation to get to the desired perfume. Especially if you think about, and this was remarkable as well, by deep learning, I think you have seen the red wine decantier, or it may be just for flowers a vase. So in this sense, you essentially also have this bias that we humans have, because some people may prefer red wine, they immediately see the decantier, and maybe others that like more flowers see the other type that was assigned as text. You just put both in the database, and with this you already kind of circumvent the bias in humans really having, let's say, a tendency to this or that. So which was an interesting aspect here of that as well. And then I think a remarkable other part was it then introducing clustering, right? Because shapes are not enough. As you heard, we also want to have the predominant color, at least in this perfume. And again, gold was a good example, but I think this is also an interesting thing that you can use clustering for it, an unsupervised learning algorithm, just for that. So in a way, to solve practical problems, I think, and this should be just a concluding remark before we go to some questions here. Also, please do some questions, because we have a chance here of a PhD student that can tell you something how life of a PhD student is. But this is really what you do in practice. You cannot throw deep learning on all the problems. I know everybody is saying deep learning is a big hype, is a new technology, and it's true, has done lots of things, but there's still lots of other applications for the traditional algorithms as well. And that should you always bear in mind when you basically go to the market after this course. So in this, I think I stopped the recording here. We're thanking Chadi again very much for this nice, interesting lecture. And we see us next time then with lecture 12 in the containers.